So this is about the PySCF package, which was developed like almost 8 years. And for whom may first hear about this library, so what is PySCF? So basically, it's a quantum chemistry package. So what is quantum chemistry? We know. So basically, it's using quantum laws to research chemistry problems, and we're trying to solving the Schrodinger equation. I'm not going to talk about the details of the science, like how to solve those equations, but basically, you just need to know that we can use certain Python tools or certain numerical libraries to solve the quantum equations for chemistry problems. Basically, then in using PySCF, it's a native Python module to solve those quantum chemistry problems. Here are some examples showing below that you can just use PySCF and to do certain ground state calculations, excite state calculations, or even like to optimize the preferred geometry for certain input molecules. That's just a first view of the library. And then now let's take a look at what the challenges in the quantum chemistry problems or the quantum chemistry programs. There are actually hundreds or maybe even thousands of famous or infamous quantum chemistry programs in the world. And I would say that for most of the programs we developed before, the three challenges every program's facing is the accuracy, the efficiency, and the whether they are user-friendly. Maybe we can even conclude that this also the challenges for any chemistry research, chemistry simulations research. So to solve the accuracy issue, probably the best way is to develop new theory and algorithms. And for the efficiency, sometimes we consider what is the best implementation. And for the user-friendly part, I would say it might be two relevant stuff. One is how to easily understand the method or understand the simulation. The other is how to easily use the program or use the library to carry out the research. And so let's see what Python, the PySCF program or the Python programs can do in the research of chemistry, quantum chemistry problems. So let's take a look at the most simple model in quantum chemistry. Presumably, some of you are experts, but let's just take a look at the simplest problem, like the Hartree-Fock model, which is the 101, which is the model we learned from the 101 quantum chemistry class. So basically, you can see in this code script, we can basically solve the Hartree-Fock problem. Of course, it's a very naive implementation, and there's no any advanced tricks used here. But anyway, we can assume that we are able to study a new model using just Python in a few of lines, like in this example, like doing the Hartree-Fock model. It's not necessary to be super complicated. We just you can write everything in Python. However, it might be slow. So that's always the challenge in the Python or in the quantum chemistry programs, that how do you make the code faster while keeping it user-friendly. I will touch this later, but basically, what do we need to study a new method in quantum chemistry? The most fundamental quantities we are carried about basically Hamiltonian and the wave functions. So in PySCF, there are APIs to access those quantities. For example, if you wish to get the coefficients of the orbital, just one line of the code as this example shows. Basically, it's what the key arguments or key variables here is the MO coefficients, MO underscore COEFF, this part. So it's a NumPy array, and you can manipulate this any way you like. There's no advanced tricks or symmetry enabled here. And of course, you can access the configuration interaction wave function. That's sort of advanced concepts in the quantum chemistry technology that's bring more physics inside the wave function. And in this example, you can see that accessing the configuration interaction wave functions just another line of code. Then to access the Hamiltonian, there are a bunch of ways. For example, to access the so-called PySCF or MCSSF Hamiltonian, there are APIs to do this job, and you can find it in the third line of the this slide. That just two statements, you got the one particle part or the two particle part of the Hamiltonian. And one of the difficult part in the quantum chemistry fields is that the two electron Hamiltonian. In most systems or in most real systems, it's a large tensor. And of course, if you don't care about the memory consumption or the computational efficiency, just need something like the n-sum provided by NumPy. The notation here is just like n-sum notation. It involves a 4-index tensor and four orbital sets. And the Pisceaf also provides an API to give you this quantity. So basically, we are able to from Pisceaf to extract pretty useful quantities, those fundamental quantities. But if we just have those Hamiltonians or wave functions, most likely it's not enough to carry out a theoretical research. And in many scenarios, next job we would like to carry out, it would be feed the Hamiltonian we are interested into certain packages to run some models we are interested. For example, in this case, we wish to do some Hubbard model research. Of course, Hubbard model is like the toy model in many in any sense, but I guess it's pretty enough to show the capability of custom Hamiltonian. So after some initialization of the Hamiltonian, we can simply feed those Hamiltonian to the Hartree-Fock model as shown by the bottom part of the slide, and then everything below, like the post-Hartree-Fock method, will automatically utilize those quantities. The Hamiltonian. So basically, you can just initialize. You can feed the Hamiltonian defined in your case, and let the PySCF solver to do the rest job. So another thing regularly used in the quantum chemistry is the previous example just shows how to feed the Hamiltonian for the Hartree-Fock or the ab initio model. So if you wish to do certain DFT calculations, which is slightly different requirements on the Hamiltonian. In this case, sometimes we need to custom the exchange correlational functional. And this example shows that in PySCF, we are able to do those customization. For example, you can do a very simple definition for the exchange correlation functional. One famous exchange correlation functional is B3-lip. In this case, you can just explicitly write down the B3-lip expression and let the PySCF package to automatically resolve the dependence and the explicit form of the B3-lip functional. And of course, you can do certain other type of definition, like the true hybrid functional, in which you can really hybrid two different kind of functional into a new functional. It might not be that realistic because PBE or Chem B3 themselves are basically well-developed functional. But in any sense, if you wish to develop new functionals, it's a tool. And if none of this satisfies your requirements, you can even write certain functional definition following the API convention and feed them to the PySCF package and let the DFT module to figure out the rest of things. So it's a useful tool, I guess, to develop new functionals. And we indeed see certain new functionals reported by using this interface. like certain papers published by OpenMind. They released a new functional completely from the AI training. And also, besides this Hamiltonian and wave functions, PySCF provides many fundamental provides APIs to access fundamental quantum chemistry intermediates. So you may have the question that why we need those intermediates? Basically, I would say they are the bricks to build the advanced theoretical chemistry tools. And for example, we often need the density matrix of a given method. We need an efficient way to build the Coulomb matrix, exchange matrix, or the fork build for a subsystem of the entire system if you wish to do certain divide-and-conquer type of algorithms. And we will also wish to get the wave function value in the real space, in the momentum space, and you might need certain customized integrals from a customized operator, and there are a few hundreds of operators available to in PySCF for the GTO integrals. So there are a bunch of things you can do with the PySCF APIs. So now let me take you some examples why we need those. How can we use these APIs to do some research, certain to find new science finds. So this is like a nitrogenous. These two examples was published in the recent 3 years. Once I'm not going to go to the details of those research because it's a technical meeting, and basically they are using the fundamental APIs provided by PySCF. For example, in the nitrogenous research, we're trying to figure out the procedure of the reaction between nitrogen and certain other molecules. And in this case, it's really complicated systems. Based on the PySCF package, there are more than 10,000 lines of code was developed to transform the wave function between different models, to construct initial gas, to make those different methods happy. And there are ways to analyze the wave function. And it turns out it's quite complicated, but it's actually gets certain useful results. And recently there are another really challenged problem that's to use the ab initio methods to study the real superconductor material. In this research, they are even more complicated the setup to do certain embedding problems, to control the convergence, and bringing certain MPI code to make the code at least working for more nodes. And this work was developed in the past like 5 years with like 30,000 lines of code on top of PySCF package. So in any of those examples, I just want to show you that in the modern science, modern research for the chemistry simulations, there's no simple setup to get a useful result. Maybe like 20 years ago, we can just run a simple model like a DFT calculation, a TD-DFT calculation, get certain results. But nowadays, there are no simple questions left. And it often requires to certain part of coding and modeling based on other tools and libraries. So that's why PySCF has been used in those challenged scientific questions. And we just talked about that another challenge in the quantum chemistry program is the performance. And you may have the question that, okay, so if this package is written in Python, as we know that Python is famous, it's not really famous about like the slow performance. Nobody will really say that Python is good for performance unless we do certain low-level development based on like C++. So that's also the tool used in PySCF, that if we do everything in Python, yes, it's happy to develop new method, but it's indeed slow. And that's why we actually put a large effort on low-level optimization. Certain code was heavily optimized, even for the specific CPU architecture. For example, the AO integrals, the fork build functions, integral transformation. Those things were heavily optimized against the hardware architecture. And other tricks also used to speed up the performance, like some asynchronized treatment on the I/O and the computation, and certain memorization or caching certain results in the module. Of course, it will consume more memory, but in certain case, they are also give certain speed up for the package. And for the Python and the C interface, we use C types. Before using C types, we actually bring out certain other experiments on like the Python, like the Python C API, but none of them really fit our needs, and the C types turns out the solution enough for the integration between the Python and the C. And there's some statistics of the code we developed in the package. Mostly they are Python, although it's not really 90% Python and 10% of C. But considering the Python has more is more expressed, can be expressed more efficiently. So we can we can consider that the part the code of the module we implement in C is really a small amount compared to the code implemented in Python. Okay, so there is some rough number of the feasible sizes in the Pisceaf package. We are now able to handle like 10,000 orbitals in the main field calculation and a few thousands of orbitals for the ab initio and the post-hard-fork calculations. And the largest systems we treated so far is even 100K orbitals. But in this case, we need to using the certain symmetry in the periodic boundary conditions. Okay, so this is a summary of the Pisceaf 2.0 features. Roughly speaking, we have set up all the necessary quantities or models for the molecules. And there are certain things we wish to develop for the periodic boundary conditions, especially how to make the ab initio periodic boundary conditions more efficient, and how to get the wave functions and Hamiltonians from periodic boundary conditions systems more conveniently. And this should be in the new release, but the release is a little bit behind the schedule, so there are new features we developed in the last year. This is including some non-collinear DFT treatments and some new correlation method called ADC method, and the new molecular dynamics module, and a huge speed up in the PVC exchange code. And right now we have been developed quite a large ecosystems on top of Pisceaf package. There are tools released with the package like full side dump, modern, CubeGen, etc. That allows you to use Pisceaf with other packages. And there are plugins and extensions like MPI plugin, GPU, automatic differentiation, demerge, and other plugins to help we study more complicated or larger systems. And also Pisceaf was integrated into other tools like the quantum computing package, OpenFermion, Qiskit, and certain machine learning packages like DeepMD, etc. So there's just a few examples of the plugins like MPI for Pisceaf. It was developed to ensure that the MPI code will work almost the same way as the serial version of the Pisceaf main branch. In this example, you can see that it's only a small difference in the import statement, which ensure that the MPI just need to be certain modules just need to be imported from MPI version, and you can just run MPI run for the MPI version. So you may have the question that how does it work? The basic idea is that in the MPI implementation, we try to use as much as possible from the serial version, and distribute the code and the data in the MPI version. So in other words, the MPI version doesn't really implement a very different algorithm. It just dynamically dynamically serialize the function and the data, and deserialize those function and the data in the worker. And those MPI workers was actually just a Python interpreter running on different nodes. When they receive the request from the main processor, it just decoded the function and the data. Our testing shows that the decoding time is almost negligible. So there's another tool, GPU for Pisceaf. It's actually not really released, but it's in the stage of releasement. There are some technical details were not completely solved, and there's a Pisceaf dev meeting in the end of this month, and we are about to discuss how to release this code. But basically, you can consider that GPU for Pisceaf is almost available now, and the way to use the GPU for Pisceaf is quite straightforward. Basically, you can choose to run them individually or run them as a drop-in replacement for the Pisceaf built-in modules. And the technique used behind the GPU for Pisceaf library is basically the integrals was implemented natively in the CUDA library. And for other parts like the tensors operations, we use QPy. So there are some future development plans here. First of all, we wish to get more. We wish to support more tools for AI research, especially for example, like the automatic differentiation technique, like the GPU plugins, and we wish to targeting larger systems. And there are requests on GitHub about the like the diagram plot, and we also consider this to be certain developer thread. As some of you may know that Pisceaf community is sort of loosen. It's not that organized. So it's also another thing we wish to develop better in the future. And in the end of this month, there's going to a annual Pisceaf developer meeting. So if you wish to know more details about this meeting, you can visit the GitHub issue, and it will all those things like the plans and the organizations will be discussed during this meeting. You're welcome to. There's online streaming. You're welcome to join, attend the meeting from online streaming. So there are some installs and the docs available for the Pisceaf package, and so basically that's the tool. If you wish to study the quantum chemistry problems. Thank you for your attention.
Thank you. Great presentation. If I wanted to get a just basic understanding of how this could help me optimize a chemical problem or chemistry problem, where would be good sources of information to learn more about that at a basic level? Yeah, so I guess, I mean, I don't have a PhD in chemistry, so where would be the best place to start understanding how to use a tool like this? Okay. Are there any relevant case studies showing how somebody's used this to optimize a business problem? Yes.
I don't have to look it here, but I just know that there are companies, IT companies in this field who do AI-driven Python to
Okay, thank you.
Any other questions?
Yeah, how far along is the ab initio molecular dynamics BOMD coming along?
Yeah. Thank you. I'm not able to give a very accurate estimation because it's a new module just joined the package. So I assume it cannot be run very long time. I guess it will be like a start point to do better things.
Hi, thank you for the talk. I was just wondering, you mentioned automatic differentiation. So what parts of PySCF will be automatically differentiable, and like what's your favorite use case for using AD in DFT context? Thank you.
Done. The automatic differentiation was developed for a few modules like touch fork, like the couple cluster, but not many modules available so far because the cost of the memory is very huge. So we developed this module just wish to provide the consistent APIs so that it can be called inside the other machine learning libraries. Otherwise, it's just not able to be used by, for example, Torch.
Any other questions? I have a question. What's the largest system that has been run with PySCF?
Largest systems. In my tests, it's like just a crystal with thousands of K points. So that shows like 100 K orbitals. But in the molecule, I know some people running more than 10,000 orbitals for the 10,000 orbitals for the DFT. For the cup cluster, it's like 3,000 orbitals, roughly. Well, it takes time. Like the DFT, every iteration takes 1 day. That's what I heard. For the cup cluster, it has to be parallelized over MPI nodes. That's not that long. It's probably like 3-4 hours. Yeah, because you're using like 20 nodes, you have enough computational power.
Yeah, let's thank Qiming again.